See if we can finish up here. So again, plugging in Gibbs equation, these expressions, here we are. Change in entropy we can describe this way. And let's integrate both sides of this equation. So if I integrate ds from state 1 to 2, that's just S2 minus S1. That's going to equal, let's do this one, well, let's just leave this one alone first. Let's say we're going to integrate, because this is with respect to temperature, so I'm going to integrate from T1 to T2, C sub V, I'm going to write dt over T here, plus, and then I'm going to integrate R dV over V. Well, the R is constant, so that comes out of the integral. And then I'm integrating dV over V. So if I'm integrating dV over V, well, that's just natural log of V. And I'm going from state 1 to state 2, so this just ends up being the natural log of V2 over V1. Kind of like what we did back up here, right? Ends up being, up here it was I'm integrating dt over t from t1 to t2, so it's natural log t2 minus natural log t1. Doing the same thing here, I'm integrating dv over v from v1 to v2. It's the natural log of v2 minus the natural log of v1. Logarithmic algebra tells me I can just take the quotient, and that replaces the difference. Okay. And then I can probably do the same thing here that I did up here, right? See what I was doing here? I said if I assume that the specific heat is constant, I pull it out of the integral as the average value, and then I'm just integrating dt over t. So that's what I'm going to do here. So I'm going to say this is approximately equal to C sub V at the average temperature times the natural log of T2 over T1 plus R ln little v2 over little v1. Those are specific volumes, not speeds. Okay, that's one form of Gibbs equation. For ideal gases. Let's look at another one. Well, actually, I'm not going to derive the same one, right? So I'm going to write this where you can actually see it. I know it's kind of hard to see that. This is really important. Delta S for an ideal gas, for an ideal gas, that's really important. Do not do this for R134 unless you just know it's vapor in both states, which is a really terrible assumption most of the time. So if it's air, oxygen, nitrogen, something like that, delta S, we can assume those are ideal gases. So delta S is approximately equal to C sub V at the average temperature times the natural log of the ratio of absolute temperatures, T2 over T1. Use Kelvin or Rankine here. Do not use Celsius or Fahrenheit. Plus this other quantity, the gas constant, times the natural log of specific volume 2 over specific volume 1. Okay? Now, I'm not going to derive the other version. I think you can probably see it though, right? Back over here, this is Gibbs' equation. Delta S or ds is equal to dH over T minus V dP over T. And if I substitute in dH here, C sub P dt, and I substitute in here V over T for R over P, and we get almost kind of a mirror image, a very similar expression we can derive up here. Also, delta S, S2 minus S1 is approximately equal to C sub P at the average temperature times the natural log of T2 over T1 minus, in this case, R ln pressure 2 over pressure 1. Okay, so let that sink in just for a second. Again, what does this do for us? The whole goal, this is Gibbs' equation for an ideal gas. Gibbs' equation for an ideal gas. The whole goal here was to determine delta S. What are some ways I can determine delta S? Because that goes into, why is that important? Well, that's the second law equation, which is over here. Sheet 1, second law equation. I need to be able to quantify delta S. sometimes I need to figure out what else is going on over here. Maybe I'm looking for the heat transfer. Then I need to know delta S, and I need to know something about the entropy generated. Then the heat's the only unknown. I can actually solve the second law for the amount of heat. That's not uncommon. And then I can plug that heat value back into the first law. So why do I need to be able to find delta S? Well, because delta S then can plug into the second law. Right? S2 minus S1, these are little s's, is always equal to the integral of del Q over T plus little s gen. That's always true. What I'm saying is if it's an ideal gas, I can use this, either one of these, to approximate the left-hand side. And then use that to try to figure out if heat is my only unknown, if I've got heat at a constant temperature, and I can pull this heat as my only unknown out, if I know this S gen, then if I can quantify this, heat becomes my only unknown, I can solve for heat transfer here. That's really kind of where we're headed with this. And that's what you'll see in some of the problems. We'll apply Gibbs equation to some problems here in the next, probably the next lecture. And that's plenty for today. That's like 5 or 6 videos already. So anyway, email me your questions, leave me some comments, tell me if these are working for you or not working for you. I don't know, just I like hearing from you guys, and I'm not seeing it in class, and I'm not getting that, so let me know. All right, guys, stay safe out there, wash your hands, stay healthy. I really hope you're getting through okay. You're going to hear a pop here, and I'm going to turn off. Good night, guys.